Back Bay Amateur Astronomers. Good evening, everyone. Thank you for coming out. We've got a great presentation scheduled for this evening. Our presenter has not yet joined us, but I trust that he will. In light of that, since we have an outsider joining us, we're going to try and go much more aggressively on schedule than I sometimes slip. So without further ado, I'm going to go ahead and start by first welcoming you. Welcome. And then my second, addressing you a little bit of administrative business so that you don't get lost next month. The fine folks in the TCC physics department were able to secure us a room. As you know, we meet in the university, community college university. They have classes in various locations. Over the course of the summer, this room is going to be in use for other classes. So if you show up here this time next month, there will be somebody who we don't know teaching a class that we're not sure about. Instead of that, they have directed us to room JA12, which is downstairs, basically which has no reference to the people who aren't in the room, but you'll figure it out. We'll change the thing, and I'll put it in next month's call out that we're going to be there, and we will also be able to be in that room for the summer and into next fall. Next winter, we'll find out when we're a little bit closer to time. So room JA12, same building, first floor. It's the second door on your right as you come in and around. So no risk of George and others getting trapped in the elevator. All right. So with that said, I'm going to go ahead and turn the floor quickly over to our vice president to go over the events of the month. We're already logged in with the calendar called up.
Who is this guy?
Moving right along.
What's his name?
This guy? Yeah. That's the inimitable
George Reynolds.
I'm a Jeff. One of the Jeffs. Jeff Thornton's here too. I do have an announcement before this is an important event too. 2 nights ago, was it 2 nights ago? 3 nights ago, Jeremy joined the dark side. He's got an S30. S50. What am I saying? S30. Anyway.
I still like
good
my
for
eyes
you.
on telescope.
Good for you, buddy.
Next one's a solar.
Oh boy.
Good luck paying for that.
Oh yeah.
Solar.
I just messed up. I got to get the share thing. Where's my share thing? Where's my share thing? Okay, got to get my share thing. Here's my share thing. All right, here we go. Now, this Saturday and 2 Saturdays from now, we have Astronomy Day in Portsmouth. Both of them in Churchland. This one's Church. Well, maybe, yeah, it's Churchland. It's in Portsmouth. I was thinking of another Portsmouth. Churchland's in Portsmouth, and so is Portsmouth Library. So both of those are astronomy days, and I think we've got one maybe. I think I can make one of them as a maybe too. So I'm going to have to really stretch it. So I'll be sending announcements out for those 2 to make sure you're aware of them this Saturday. And basically, it's here's what we do, and here's the stars, and we'll set some solar scopes up outside. It's during the day, of course, 11 o'clock. So if you can make that, please do. Boardwalk Astronomy number 1 this Tuesday, 6 p.m. Now, why is it so early? Since the sun doesn't go down until 7:30, you might ask. Well, we have to see the sun and get the crowd, hey, what are you guys doing here? It's really fun to go to Boardwalk. So please do come to Boardwalk, especially if you've never been. It's on 24th Street, I think. 24th Street by the lifeguard station. And it's amazing what our telescopes can capture, including the wind turbine that's out there 26 miles. You can see the top of it, barely, in the water, Earth's curve. This is for flat earthers. It's a deal breaker. All right. Garden Stars on the 8th. And that's a big event. I haven't been to any of those. George does those a lot, and I haven't done to any of them, so I'm going to make a confession here. Saturday, Sunday, the 10th is a lot of fun. I think we ought to get together and do something Saturday, Sunday, such as a solar thing. Is that coming up? We're going to try and do a solar filter workshop. Okay, Saturday, good.
Weather permitting.
Weather permitting, of course. Corn Watch, and these 2 Corn Watches are generally for the people that are serious astronomers that don't like laser pointers. They would rather have images without laser in the way and things like that. So if you like to do that, that's what Corn Watch. That's an exclusive for us. That's why it's in green, I guess, isn't it? Skywatch and Portsmouth Library is going to be tough that day. I'm going to try to make both, I think, but we'll see. We'll see how tired I am. But Skywatch is fun. That's at Northwest River Park. Please come out to that. I think that's probably the most attended for public beside Boardwalk Astronomy. Boardwalk Astronomy is we get like 200 people every time, but Skywatch probably get 100 or so, sometimes more. Cortland again, 23rd, Night Watch, Chip Oaks is the 24th. All right, moving right along with my next month. And as Jeremy said, we're going to meet next time downstairs at JC12, JA12. See, I'm so used to JC.
Topic for next month, we've got folks from the Citizens for Responsible Lighting in Norfolk that are going to be coming out and talking to us about their dark sky initiative. They're a partner with Dark Sky Virginia
Very good.
and the International Dark Sky Association. Apparently, the city of Norfolk is in the process of revitalizing and replacing a lot of their civic lighting. They are lobbying, working with pressing the flesh and trying to get the city to make choices on lighting that is more friendly to the skies, more friendly to the pollinators, more friendly and safer for the populace. Because as it turns out, bright blue lights in the middle of the night don't actually make you safer, it just gives you the illusion of security.
The illusion of security. I like that.
Security theater.
There you go.
Wherever you go.
Just a reminder, Boardwalk Astronomy has a first quarter moon. One day beyond it, maybe we can see the wall. I don't know, there's a wall on the moon there.
You're still in May.
I know, I just wanted to go back and look at that, because the following month again is first quarter moon in June, and that is first quarter. So we're really going to see the wall first quarter. There's a wall on the moon there. You can see it in a certain spot when the shadow's just right. So that's a nice one to look at too. And we already said Thursday's going to be downstairs. We got a bar mitzvah star party that I probably will go to. I don't know if anybody else wants to go, but that'll be kind of fun. And that's at 7:06 p.m. Why 7:06? I have no idea. Garden Stars, Saturday, Sunday, the following Saturday. Anybody new here that doesn't know what Saturday, Sunday is? Because I had some people. Okay, good. I'm glad you mentioned that, because Saturday, Sunday means you look at the sun on Saturday instead of looking at the sun on Sunday. Otherwise, it'd be Sunday, Sunday. Okay, did I confuse you?
It's some kind of play.
It's a Saturday, Sunday. It's kind of a play on words, kind of, but not exactly. I thought it was a catchy name. I didn't pick that.
Put the sun in.
That's cute, I like it.
It is pretty cute. Yeah, it's pretty cute.
It's one of our recurring.
It's a Saturday, Sunday.
Did Sean pick? Did you pick that, Sean? Remember, you know the history of that? Anyway, it's a good idea.
Just put it close.
It's a good idea. Yeah. All right. Well, where are we? Juneteenth is the 19th. What is that? The 19th, Juneteenth. What's the deal?
It's a federal holiday.
Federal holiday. There you go.
Holiday. Just throw it in there.
Technically, they
Okay.
all are. So
Skywatch on the 21st again with Northwest River Park, Corland, and Night Watch again at Chip Oaks. Any questions for me? I have ID cards for some of those people that didn't get those. Perhaps if you're new to the club, I didn't get the very, very latest update yet. I tried to get it from, he probably sent it to me. Rich, did you send it to me? I don't know if you did, but I did.
Roster.
Yeah.
Yeah, I sent it to you last night.
Okay, of course, I didn't look. Anyway, thank you very much.
thank you, Jeff. All right, next, and I'm going to turn the floor over to our illustrious treasurer, Rich Roberts, for a hopefully fairly brief treasurer's update.
It will be brief.
Brilliant.
I gotta switch to share. It didn't stop sharing.
Am I the one? Okay. Oh, that's the. There you go. Over to you.
All right. Share screen.
I didn't bring the volume up.
All right. So we got $16,015 across all funds. That is a decrease of $31 from the previous month. So not a lot of movement in the funds. We had very few transactions, and mainly just some money coming in on like Georgia June ticket sales, and then some just normal kind of expenses. So not a whole lot to report on. We had 0 members join in the month, so we're at 181 is where we were at the end of last month. That's like the first time I think since I've been treasurer that we didn't have anybody join over the course of a month. So that's all I got. Not much to discuss. The first quiet month we've had. I was
Fair
grateful.
All right. Any questions for the treasurer?
Was it in the black on field day? What is it? Chip Oaks. Are we in the black on Chip Oaks?
Broke even.
Broke even, check.
Brilliant.
Yep, right where we kind of wanted to be.
Entertain a
motion to accept the treasurer's report.
Second. All right, moved and seconded to accept the treasurer's report. All
Aye.
opposed? Excellent. Treasurer report accepted. We'll enter, Gabe, I'm turning over the floor to our illustrious secretary for a.
Move to waive the minutes.
There's been a motion to waive the minutes
Denied.
and seconded.
Discussion.
Any, all in favor of waiving?
Okay, to be fair, if there was ever a night to waive the minutes, it's tonight because
We have an
Sean didn't upload the doc to the meeting.
Ouch. Okay, that's mean spirited.
Okay,
But
okay,
true.
it's not his fault. He didn't have internet. He didn't have
All right.
internet. So-
All in favor of waiving the minutes and grounds that we have,
Aye.
all opposed? Excellent. Thank you all for being, supportive.
I'll just double up next time.
That's, we stand warned. All right. Next, I'm calling upon the inimitable Bruce Powers, our astronomical league coordinator and East Coast Star Party chairman, who's joining us in Zoom land because he is in pain.
Yes. I'm recovering from injuries incurred during my vacation.
I thought the pain was managing your employee Jeremy. That just causes you lots of
Well,
pain.
that's
Managing
its
is a
own
strong word.
that's its own special pain. I have to see counselors for that. So Jeremy and I negotiated the fall Star Party date for the East Coast Star Party as September 18 to 21. Okay. Thank you to Sean for already updating the website. Before I get attacked on why we chose that date, what I would say is, okay, that is the new weekend for September, and the October dates, we intentionally deconflicted this time with the Staunton River Star Party, which runs the 20th through the 26th of October. So this fall, you can go to our Star Party and then drive out to Staunton River and attend that. It is not the weekend of week 17, 18, 19 October, because that was already booked by Chip Oaks for their fall festival. We got the September date, fortunately, because the Nottoway Indian tribe decided to, forfeit that weekend. So we have scheduled with Trevor Johnston the Ranger September 18 to 21. So book your campsites and book your cabins now, because they too tend to book up for the fall. Okay. So I believe Sean posted on the website that the registration will open in June. Okay. So can I share, or do I need some special?
You have the power.
Chair, but I do request, as Dr. Law has joined us, I do request that we be relatively brief with the remainder of our business.
Okay. All right. So in the brief remainder of my report, so there is nobody from our auspicious club in the Reflector for Observing Awards. This is the digital only edition, and I would look forward to seeing some names from our club in the June edition when that comes out. As always, the Astronomical League site is here. One of my favorite things to do is to go to their new handouts and also look at their star charts for each month. So those are all posted there, and these are all PDFs and they're easily printable. Okay, so that's all I have.
Thank you, Bruce. And on that subject, I think you'll be pleased in what's coming up. Next order of business, before we turn it over to him, on the subject of the Astronomical League, I received a piece of mail addressed to the club on behalf of a Mr. Benito Loyola. I could have Ben come join us up here. Well, Ben has been recognized for an Astronomical League program, the Asteroid Observer Program, which comes with a not exactly full color certificate, as well as a pin that I have not tried to open from in there because I don't want to destroy it, as well as a citation. Dated the 30th of March, dear Benito, congratulations on observing 100 asteroids in at least 2 positions and earning your Gold Asteroid Observing Program Award certificate and lapel pin. It was a pleasure to review your asteroids. The image on the certificate is the main belt asteroid 4 Vesta. The image was returned by the Dawn spacecraft, which orbited Vesta from July 2011 until it left orbit in September 2012. Has an average diameter of 525 kilometers, the brightest asteroid we've seen for Earth. Congratulations to Ben on a job well done. Congratulations, Ben. I'm going to shake your hand and present a certificate like this. Well done. The Astronomical League coordinator is giving us spirit fingers and is reminding everyone of the joy of accomplishing these Astronomical League programs. And with that, since you're already up here, first of all, another round of applause. Oh, pause for the shake. We'll put it on the website if you're all right. All right. It is. Like this. All right, great. All right, so congratulations, Ben. Another round of applause. And on that note, I'm going to give you the podium for the scholarship.
Oh, just real quick, scholarship and welcome the new guest. Just a reminder, our astronomy club is a 501c3. It's a nonprofit education organization, so donate away, tax deductible. And for our size, we give away a amazing amount of money and been done so for many, many years now. So we have 3 scholarships that the closing date is today. So hopefully we have some applications. We've had 1 year in the history of BBAA that no one applied to, and the next year rolled over and something like that with good money. So we have the Back Bay Amateur Astronomers, which I believe is $2,000. The Georgia June Memorial Scholarship. Georgia June was a wonderful member of our club for many years and gave so much, and unfortunately she left us way too early in life. And that was $1,500. And then we had the Nick Anderson, another member of our astronomy club, also in memorial for him. And that's supported actually through the city of Virginia Beach for $5,300. So we're literally giving away almost $9,000 worth of scholarships here. And we give them away. We rank them based on their grade point average, their SAT, ACT scores, a 500-word essay, as well as a teacher write-up. So we'll be doing that. We'll be screening the applications. Pray that there are some in May, and then try to get them to the next club meeting in June. Here.
Next club meeting in June is here. Yes.
Perfect. So, and we asked them to read their 500-word essay. So,
yes, can testify. They will ask you to do that.
If we get no applicants, then we'll just have Gabe read his again.
There you go. I think I got it on this computer still.
And that was asked earlier too. I'll reiterate. Yes, kids, grandkids, great-grandkids, neighbors' kids, please encourage anyone to apply. Senior, into some type of astronomy or science. Obviously, not all schools have astronomy programs, so they just got to write their passion, love for science. So, pretty cool. All right, thank you.
Thank you, Ben. Congratulations again.
Thank you. All right, more to come.
On the subject of scholarship, not in the sense of monetary scholarships, but in the sense of what scholarship can do, I'm about to introduce Dr. Law, who's our guest speaker for this evening. I do want to thank everyone for coming out tonight. We've got a great turnout here in the room. Dr. Law, I don't think you can see them all yet. We have some first timers. Thank you. Welcome. Is anyone here for the first time other than the 2 folks that I recognize that walk in? All right. Well, thank you. Hopefully you're in for a great opportunity tonight. I'd like to, as mentioned, introduce Dr. Charles Law. He is a NASA Hubble Fellowship Sagan Fellow at the University of Virginia, previously at I believe, Cambridge University, Dr. Law?
Yes, yeah, I was at the Center for Astrophysics associated with Harvard up in Cambridge. Yep.
Oh, excellent. So thank you for joining us tonight. Dr. Law is going to be sharing some of his work. He's studying stellar chemistry and the formation of stars and planets. Is now a good time for you, sir?
Yeah, I'm happy to go ahead whenever everybody else is
Out
ready.
of respect for your time, I'll go ahead and turn the floor over to you. We'll suspend the rest of the business of the meeting until afterwards and give you the floor. Thank you, sir, for joining us.
Okay, wonderful. Bill, thank you so much. I appreciate that. Let me go ahead and first share my screen and let me know if you can see this. Okay.
We have your screen. I'm going to go on. I'm going to
Okay.
put this on mute so that we don't drown you out.
Okay, wonderful. Well, thank you so much for the introduction. And I want to just thank the entire Back Bay amateur astronomers for having me for this opportunity, for an opportunity to share with you some exciting science that I'm working on. As was mentioned, I'm currently a postdoctoral fellow working at the University. I'm sorry, I'm joining you virtually. You're not that far away. I unfortunately just couldn't make it down. But still really happy to be here tonight. And so my main research focus is I'm a radio astronomer who studies molecules in space. And so I thought an apt title for a presentation would be to tell you a little bit about the molecular side of the universe and how we can use something called astrochemistry to understand the cosmos. So I guess with that, let me just get started. So first, big natural question. It was in my title, what is astrochemistry? And so I just want to start here with a quick definition of this very broad field of astronomy and astrophysics. This is the study of the formation, destruction, and behavior of molecules all throughout space. So any type of molecular chemistry, molecular physics going on out there in interstellar space, we call astrochemistry. And in particular, we like to use these molecules to understand something about the physics, to understand something about how molecular material can influence the structure and evolution of all these astrophysical objects that we love and we care about, such as how does this impact stars or planets or galaxies and so forth. But really, it is just molecules. We're looking at molecules out there in space. So one big overarching question that you might have is, why should we care? Why is it important to go out and study molecules out there in space? And so one image I always like to show here is just this very beautiful artistic rendition of a spiral galaxy here, where you can see in blue the spiral arms. And if you look at the closest arm towards us, the artist has made this in the form of a DNA double helix, which is just underscoring the cosmic connection we have. The only reason that we're here, the only reason that life exists is that a very particular set of circumstances had to happen to enable life. And much of those circumstances needed to be molecular chemical ingredients that allowed life to end up forming. So I think in that sense, there's a very deep connection between the chemistry, the molecules that are out there in space, and us that are also made of the very same molecules and constituent materials. So one of the most fundamental questions that we can actually get at by studying molecules in space is really this idea of our cosmic origins. That is, how did we get here? And we can really begin to directly probe this question. We can go out and ask, do we see similar molecules, prebiotic molecules, those that would allow a life to eventually form? Can we detect them out in other solar systems, out in interstellar space? Here is just one particular example in which you had potentially the delivery of prebiotic molecules from comets onto a young planet such as Earth. Beyond this question of cosmic origins, say you don't care deeply about this, origins, where we came from. Say you just want to do hardcore physics. You want to understand what's going on out there in the cosmos. It turns out using molecular emission, using molecules, they give us a wholly new view of physics that is going on. And to just underscore that point, this is an image of a galaxy here. So this is a real image from a real telescope. You can see spectacular spiral arms and all kinds of structure. But this isn't visible light like you're used to seeing with your eye or with the Hubble Space Telescope. This is actually a molecule. This is light coming from a particular molecule, the carbon monoxide molecule. And this tells us a whole new set of information about the gas that we can just not see in other wavelengths. So I'll come back to actually how we actually make an image like this a bit later on. But that is to say, molecules also tell us a huge amount about the physics that's going on in space. Okay, so I just want to show you a quick gallery of all the different astrophysical environments in which we have been able to detect molecules and use them to learn something about the physics. The first and the nearest and dearest to my heart is planet-forming disks. So protoplanetary disks, that's the environment in which our own Earth forms, in which all of the exoplanets that you've maybe heard about formed in. We can look at their gas composition and make beautiful images like this. We've also been able to detect molecules in the solar system and other bodies, such as comets. We're also able to use molecular chemistry to actually map out the structure of our own galaxy and other galaxies. We're able to tag the chemical composition of molecular clouds, the environments in which stars form. On the other end, we can actually use molecules to trace stars that are dying. And in fact, we can even use molecules to watch the aftermath of a supernova explosion. So what this really means is that there's not an area of astrophysics that cannot be informed by leveraging a carefully selected set of chemistry and a carefully selected set of molecules, from the very birth of planetary systems to the very death of stars. Okay, so now to dive a bit into the details here. So when I say astrochemistry, molecules in space, what I mean is really this part of the graph. So I'm talking today mostly about the interstellar medium, that is the stuff between the stars. So there's a lot of exciting chemistry that goes on within our own solar system, of course, here on Earth, but throughout the entire solar system. But today I'm just going to be focusing on that which is beyond, into the interstellar space. So that interstellar space is something we call interstellar medium. It's the stuff, all the matter and all the radiation that exists between different stars out there. It's 99% of it is in the form of gas, with only a very small fraction being dust. So 99% gas, 1% dust. Turns out, as I'll touch on a little bit later, that 1% of dust actually makes a huge difference. Without it, you wouldn't actually have a lot of this interesting chemistry. But by just total mass, most of the stuff between the stars is gas. But that might seem like a simple picture. Okay, it's just all this quiescent gas sitting there cold out in space. But that's not the case. If we look at certain areas of the interstellar medium, what we see is a very complex and multi-phase picture, such as what you can see here in a really spectacular image from the Hubble Space Telescope of the Orion Nebula. So I'm sure many of you are familiar with the Orion Nebula. This is an area where we have lots of gas and dust together around forming massive stars. And what this means is in a relatively small area, we have gas that is ionized, we have gas that is atomic, gas that is molecular, just depending on what kind of environment it's surrounded by. And you can just see this directly in the image here. These dark lanes here, this is dust. In the center, you have these massive young stars putting out a ton of radiation that is dispersing, that is destroying the nearby gas, that's ionizing the nearby gas, putting out tons of UV light, and lots of charged particles that are all swirling in this relatively small area. And then if you look a little further out, there's some portions of dense gas that have yet to be totally disrupted by these young massive stars. So that is to say, all of this swirling material is happening in a really smallish area. And if we zoom in here, we can actually see the consequences of this in detail. So if we zoom into the middle of the Orion Nebula, this is a beautiful image from the James Webb Space Telescope. It looks almost like an artist's rendition with all sort of abstract colors and swirls here, but this is a real image. And what we're seeing is on the right in orange, this is the molecular material. On the left in blue, this is the ionized gas. And in between this, what you can see is a very clear line that divides these two. That divides the ionized on the left and the molecular on the right, something we call an ionization front. And what we can directly see in these observations is that there are massive stars here. Their light is coming in, ionizing all the material up until it hits this front, and then it hasn't fully reached the molecular material. So as time goes, what we expect is eventually this entire image will be blue. All of that stellar radiation from the young stars will push its way through, the ionization front will creep ever forward, changing all of the gas from molecular to ionized as it breaks into this material. Okay, so that's just a quick overview of how complex some of this interstellar space can actually be. But it's important to also just quickly talk about what the gas itself is made of. As I said, gas is the majority of the interstellar medium. And of that, the majority of that is unsurprisingly hydrogen. Over 90% of the gas is hydrogen, around a little less than 10% is helium, and then around only 1% is so-called heavier elements that we astronomers call metals. People like on Earth, chemists on Earth don't love this because everything that's not hydrogen and helium is historically to an astronomer a metal. And that's just because it's so rare. Almost everything we're dealing with here is hydrogen or helium, and all of the other things that we're quite familiar with, carbon, nitrogen, oxygen, we call metal. All of the hydrogen and helium is that's left over from the Big Bang. But the more interesting stuff, those so-called metals, are really coming from an enrichment process due to stellar fusion and ultimately stellar explosion. So we can actually look at this in detail. We can put up a whole periodic table, which if you're from your high school chemistry class, you can see all of the elements here. And we can color code these according to the cosmic origin of that element. So you can see in blue here for the hydrogen and helium, that's pretty much entirely coming from the Big Bang itself. But there's lots of other elements here that are coming from some version of stellar death, something involving a star exploding. You can see many of the elements that we are familiar with, we care about. So, oxygen, carbon, sodium, magnesium, all of this are colored green here. So they're exploding massive stars, produce many, many of these elements that we care about, that we need to live, that are in our bodies. So that's the green color right here. How this actually works is essentially due to the onion-like structure of massive stars. Massive stars have, as their name suggests, many times, tens of times the mass of our own sun. And what this means is that the fusion that happens in their pores allows them to reach many heavy elements. So in the center of these really massive stars, you have lighter elements being fused together. But in these very massive stars, you have things like iron in the very center being fused. And then in a shell outside of that, you have the formation of silicon and sulfur. And then a shell outside that, you have things like magnesium or oxygen. And this shell-like structure just continues as you have successive layers of fusion happening due to the large pressures of these really massive stars. And so that's why we often refer to these as sort of onion layers, because all of this is happening simultaneously throughout the life of a massive star. And you can compare this to something like our sun, which is not going to be able to fuse these heavier elements just due to its size. But what we actually know, and we have actually been able to see with telescopes, is that these are the environments that are going to then give all those materials back when they explode. The massive stars only live relatively short lives. They do all this fusion really quickly, and then they explode in spectacular, like supernovae, such as this shown here. This is a remnant of a supernova explosion, so a massive star that exploded, and you can actually see all that material just expanding out from what once was a massive star. What's really powerful here is that we can actually see in these kind of explosions with telescopic images, different elements being released back into the interstellar medium. So if we put on our X-ray goggles here and we look at this image, we can actually break it up and see the various constituent elements here shown at the bottom. So for instance, on the right-hand side, you see the iron being released back into the interstellar medium. You see things like calcium being released in green, and basically all of those elements that were then fused in the star are put back out into interstellar space, and they enrich the interstellar medium. And that's all of these elements that we need to live. That's all the elements that we need to actually do any interesting chemistry are ultimately coming from these stellar explosions. And we can actually see this process now happening in detail. So really, yeah, this is the raw ingredients that you need for chemistry to actually happen. So if I were to just ask generically, where should we go finding molecules, right? I said that there's a whole field of astrophysics called astrochemistry that studies these molecules. Where are we going to actually find them? Where's the first place to look? So here, what I'm showing is a nice overview of our own Milky Way. What you can see here is the starlight in the background, but all of these wispy regions that are blocking out some of that starlight. So these are dense clouds of dust. So if we zoom in on one of these particular clouds, so let's pick this one right here, what we might see is an image that looks like this. So these are giant clouds of gas and dust. They're so-called molecular clouds, which I'll get to in a moment, if you've ever heard that term before. But these are the birthplaces of stars. And what we can clearly see here is that the light is being blocked by the dust. So in regions where you don't have lots of dust, all the stellar light from the background just comes through. But in the regions where you have lots of dust, you can see in this almost tendril-like structure that the background light from the stars just gets absorbed and you don't see it anymore. And as I said, that dust typically is 1% of the total interstellar medium. So in each one of those tendrils of dust, you have 99% gas. We have a ton of gas in any region where you see dust like this. So these are huge, dense, cold clouds of material. But when astronomers first started looking at these, they thought, okay, they're just sitting out there in space. It's too cold. There's not enough material. It's too cold. We're not going to see chemistry. We're not going to actually see molecules. If you ask what the physical conditions are in one of these clouds, the temperature is maybe 10 degrees above absolute zero. So just absolutely frigid. The total density in terms of particles, atoms per cubic centimeter might be something like 10 to the 4th. That might seem like a lot. If you compare that to what the air is that you're breathing right now, that is at room temperature, something like 293 Kelvin. But even more stark, that density of that air around you is around 10 to the 19 particles, atoms, molecules per cubic centimeter. So you can see the huge difference here. Many, many, many orders of magnitude less dense are these clouds out there. So first, when astronomers looked at this, they thought too cold and not enough stuff for any actually interesting chemistry to actually happen. And if we convert these for those that aren't used to Kelvin, these clouds are around negative or over negative 400 degrees Fahrenheit. So incredibly cold. But that was proven wrong, thankfully so for our field. It turns out there's an incredibly rich chemistry hiding in these clouds, hiding out there throughout all of interstellar space. This is a plot here of the total number of cumulative number of detected molecules as a function of year. So the blue curve here is how many new molecules that we've found. And what you can see is that sometime around the 1940s, we detected our first few molecules. And then once we get to the sort of 1970s or so, this curve just goes straight up and it just continues to go up and up and up. And now we're at around, this curve says around maybe 200, 240. This is slightly outdated. We're around 300 or so molecules, 330 plus. So this curve has just continued to go up and up and up. And what you can see here is there's little knees in the curves here where the slopes increases a little bit more. It's labeled. Each one of these is a new telescope. So turns out anytime that we turn on a new telescope, we find a bunch of new molecules. And this is sort of borne out in the detections. So if you just do from detections since 1968, it's maybe 3 or 4 per year. But within the last decade or so, we're at 6 or 8 Now it's probably even 10 new molecules we detect per year because we just turned on so many fantastic telescopes. And to give you a rough idea of, don't squint and try to read every single molecule here, but I'm just showing a bibliography of all of the different molecules that we have detected in space according to how many atoms that they have. So we have many that are simple, many that are 2 atoms, 3 atoms, maybe up to 5 or 6. And many of these are things that we're very familiar with. So something like CO2 or water, things that, you know, in a terrestrial environment makes a lot of sense. We see these all the time. But in a few cases, we've actually been able to detect bigger molecules, 9, 10 plus atoms. And a few of these are quite strange from our perspective. Here's one such example. This is an incredibly long carbon chain, HC9N. What that means is you have 9 carbons just sitting in a line, like a giant linear molecule that on Earth would just be immediately destroyed. We don't see something like this anywhere in the terrestrial environment. So finding molecules that look like this were a bit of surprise. We also see pretty big molecules, things that are, you know, almost becoming like a dust particle. You might not even call it a full molecule. You might just call it a dust particle. It has 70 carbons here. This is a buckyball. But if we go through and we ask which elements make up all of those giant tables that I showed you before, it ends up being the usual suspects here. A lot of them contain hydrogen, many of them contain carbon, nitrogen, oxygen, and then by the time you get down to the 3rd or 4th row of the periodic table, considerably fewer. We know a few with phosphorus, a few with calcium, potassium, but really it's the things that we are familiar with here on Earth. So what I want to do is just go ahead and walk you through sort of 3 parts here. How do we actually make these molecules? How did we go from the initial expectation that we wouldn't have many molecules at all sitting out in space to finding all of these? Then tell you a little bit about how we know this. How have we actually been able to detect them? And why do we have that curve just going straight up with new and new detections? And then lastly, to touch on just a few examples of what we've been able to learn by detecting all these new molecules. Okay, so to get started, first, how do they form? So here I've just grabbed the most common elements that participate: hydrogen, carbon, nitrogen, oxygen, silicon, phosphorus, sulfur. Something we're all familiar with. What we need to ultimately form a molecule is a chemical bond. We need 1 or more of these atoms with these elements to come together, bond, and form something that is stable and can exist as a molecule, not just immediately break apart. So in a pictorial sense, you would just have compound A plus compound B makes some joint compound. Let's call it AB. This could be a smaller molecule joining with a bigger molecule, or this could be just 2 atoms that are floating that come together. The problem that we were faced with is that this compound that ends up forming AUB star tends to be quite unstable in a general sense. A lot of times this just wants to fly apart. AB star has a lot of extra energy because of the 2 molecules just hitting, or two compounds just hitting together. It doesn't want to form the stable molecule. It just wants to release that energy and break apart again. And this was one big reason that people worried, would you even have chemistry happening in space? Because on Earth, in a terrestrial analog, you have this happening. You have something called a 3rd body reaction, that you form your excited state, AB, and it immediately runs into something else. Here I called it M, but it is something like inert gas, like nitrogen in our atmosphere, or oxygen in our atmosphere. And that inert compound can take away some of that excess energy, leaving you with a stable molecule. Now, just AB by itself, it's stable, it's shed its excess energy, and then that inert compound can just give off its heat. So that's the process we rely largely here on Earth, this 3-body reaction happening. But if you don't have that 3-body reaction, like in space where the densities are so low, what's often going to happen, at least people thought, was you're going to have the first reaction. Things are going to come together, and then they're going to fly apart. So it's really hard to imagine a scenario in which in these low densities, you actually have three things coming together all at once. It's not going to happen that much. So what is the solution here? So it turns out that this is where dust comes back in. Remember, I had said that 1% of dust doesn't seem important, right? But it turns out dust particles are incredibly important because they provide that so-called third body. Here's a quick image of an interstellar dust particle that has been scooped up by one of the NASA missions. You can see it's maybe 5 microns or so in size. It's roughly human hair sized. It has all kinds of pores and structure. It's not just like this smooth pebble. What this means is that if you just zoom in on a little part, there's lots of places for different molecules and atoms to come in and hit the dust particle and get stuck. And so if that happens, if you have lots of atoms that are floating out there in space in the gas, they run into the dust particle, they get stuck in one of these little crevices here. And then with time, more and more atoms fall in, get stuck nearby or on top of the same material that's getting stuck. And it just sort of moves around. It diffuses a little bit. It just kind of hops throughout the dust particle. Eventually it finds a pair and it forms a bond. It forms a molecule then. But this case, the dust particle itself can be your third body. It can take that extra energy. It can take that extra heat for you. So you don't need 3 things coming together all at the same time. You just need things landing on the dust particle, hopping around, finding their molecular partners to form your bonds, and then giving the heat into the dust particle. And the scale here, I want to point out, this is sort of roughly to scale. The atoms and the molecules are absolutely tiny compared to this large dust particle. So it's happily able to absorb that tiny bit of extra heat. And in fact, people have built models of this. So I can show you a quick example here, where this is a computer model of a dust grain. And here, this is an atom. This is a hydrogen in white, just hopping around. You can see it just moving throughout the dust until it finds a partner. And its partner there is going to be another molecule that's already formed. And the moment it's going to hit that other partner, it's going to form a bond and it's going to stop hopping, which you can see just happened right there, right? And now it gave that excess energy into the dust. And now you have an animation of another one hopping around. And it's this process of atoms coming in from the gas, getting stuck on the dust and hopping around that slowly over time forms more and more molecular complexity. So if we were to run a full model here without just not showing you the hopping, but this is what would happen with time. If we just ran this forward for millions and millions of years, you would build up more and more molecules that would be bigger and bigger and bigger with time. As things land, hop around, form some bonds, and then you get bigger and bigger compounds forming. And until essentially you don't even see your dust particle anymore. It's just this encased entirely in chemical material, chemical bonds. So yeah, now you have a very molecule-rich dust grain right here.
Dr. Law, can I ask a question about this real quick?
Yes.
So this is talking about molecules forming in the interstellar medium itself. I have to imagine that's a very small percentage of the molecules we see there, and that most of them is probably formed more in like these stellar envelopes of asymptotic giant branch stars, and then the stellar winds blow it out. So is this like a small percentage, or is this how we get the more complex, like the larger chain molecules, like the ones with 7, 8 atoms are formed in this way? Most of the more common ones, like carbon monoxide and cyanide, those are all built in the envelopes of stars that are blown out by the stellar winds. Is that
No,
am I on the right track?
That's an excellent question. Yes, so that is another avenue for making molecular complexity. But I would say the jury is still out on which one matters more, because there's this question of top-down or bottom-up chemistry, which is what you're sort of talking about. Like, do you start with like big dust particles and break them apart and shoot out all of smaller compounds, or do you build up from the very constituent small things. And I would say that we don't know yet. It's very well that this could be dominant in general from the interstellar medium side. So it depends on who you ask.
I'm surprised by that. I'm surprised, but yeah.
They both contribute. They definitely both contribute,
Yeah.
but it depends on which chemical modeler you talk to. Will tell you which they prefer.
Well, I'm more interested now that we don't really know. I was making assumptions, of what I always heard about was the main dominant force. Interesting. I appreciate it. Thank you.
Yeah, no, that's an excellent and insightful question. Yeah, it's a big question because we keep finding more complex molecules everywhere, including in these quiescent phases. And so that is what challenged things, because people have found big molecules in these cold clouds that the only way they get there is to just build up slowly over time. So that does challenge things a bit. But the only way we actually know about this, right? This seems very nice picture, very theoretical. The only way we actually know about this is if we can go detect these molecules. And the only way that's going to happen is after we get them into the gas, because all of our telescopes, all of our detection methods rely on largely seeing things in the gas. And if you look back at this, everything here is stuck, right? All the molecules, they're stuck onto the dust grain. They are cold. They are almost like, they're mostly ice at this phase. But we need them to be in the gas to actually detect them. So what we rely on is the fact that in these giant clouds of gas and dust, eventually a star is going to form, many stars often. And once the stars form, they'll put out a bunch of radiation, just like that image I showed you of the Orion Nebula. They'll put out a bunch of radiation, they will heat things up. And what you get is something like the schematic shown here, which is all of that material, all that molecular material that's stuck to your dust grains will not be stuck anymore. It will be liberated, it will come off the dust, it will become gas. And then it will just be freely floating out there in the gas phase. And this is something we can detect. Once we get the molecules off the dust into the gas, then we can find them with our telescopes. And so that naturally brings me to the next part of this, which is how we actually go about detecting them. Once they're into the gas phase, what is the technique we actually use? And so to preface this, I can just show you a number of molecules detected per wavelength. So the x-axis here is the size, essentially the atomic mass, how big the molecules are. You notice all of the curves are kind of shifted towards low atomic mass. It's easier to detect smaller things. But just look at the numbers here by different colors. So if you look in pink, that's visible or ultraviolet, and the number there is 5. So we've only detected 5 molecules in the visible light. If you look instead at the orange color here, which is labeled millimeter, then that's over 100. And if you combine that with the centimeter and the submillimeter, then you have nearly 200 molecules detected in the wavelength range of centimeter to submillimeter. So it turns out using optical telescopes is not so fruitful, but it looks like going to radio or microwave facilities, that's where we're going to be able to detect most of our molecules. And so it's just a quick refresher. So we're all on the same page here. When I talk about these different wavelengths, I'm just referring to the electromagnetic spectrum, going from gamma rays at the most extreme, most high energy. And if we walk here towards to the right, we get to the lower energies down to microwaves, radios. And so this is the region here where we're detecting the majority of our molecules on the lower energy side of the electromagnetic spectrum. And to just give you an idea of scale here in terms of the wavelength that we're dealing with, here on the right, we're dealing with fairly large wavelengths, things that are pretty large, the size of a coin or to a person size, essentially. And this spectrum here really is just encoding how much energy you have as you're going towards the longer wavelengths towards the right. The individual packets of light, your photons, are going to carry a little less energy. They're going to have a longer wavelength. But importantly, this also encodes a bit about the temperature that these objects are. So if you're a really, really hot object, you might be emitting in the X-rays or the ultraviolet. If you're human temperature, or body temperature, you might be somewhere in the middle, emitting in the infrared. And then if you're very cold, like these cold clouds of gas and dust, you're going to be the whole way to the right here. you're going to be emitting at the microwave and the radio. And so that's a big part of this equation as well. The fact that these regions are so cold, we end up looking at the portion of the electromagnetic spectrum that corresponds to their cold temperatures. But the fundamental idea that we're exploiting here is that everything in physics, in life, it doesn't want to have excess energy. Everything wants to get to the lowest energy state that is possible. And that applies to molecules just as well as it applies to everything else. And molecules want to cool down. They want to give off their excess energy. One way that they can do this, because they actually have a bond. So if you just imagine sort of a simple diatomic two atoms bonded together, that bond, they can either rotate around the bond or they can vibrate. And which they have access to, either vibration or rotation, just depends on how much energy they have. But they want to slow down. So they want to vibrate less quickly, they want to rotate less quickly and give off that extra energy. And what we can do is we can actually see what kind of transitions from a fast rotation or fast vibration to a slow vibration or a slow rotation that is going to give off some heat, give off some energy, give off some light. And it's exactly that light that we're able to detect. But these are relatively low energies we're talking about. So that light ends up showing up in the portion of the electromagnetic spectrum that is in the cooler portion, in the radio, in the microwave. And so that is why we end up finding most of these molecules at millimeter, centimeter wavelengths, because that is where the rotations are happening. That's where the molecule vibrations and rotations are happening. And so to just go through that one more time, basically this is what we're observing. Molecules are cooling down because they want to spin or vibrate slower. We know because of quantum mechanics that this process doesn't just happen continuously. If you're a molecule out there, you just are not allowed to rotate at any speed possible. You are only allowed to rotate at very specific quantized speeds. So in this example here, you see almost a ladder of energy. If you're a molecule, you're allowed to rotate at either the 2B ladder, the 6B ladder, the 12B ladder, and nowhere in between. You can only have those energy states. And so if you want to go from a high energy state, a fast rotating, to a slow rotating state, you have to jump between these rungs on the ladder. You're not allowed to just be any energy. You have to follow this ladder precisely. And so what that means is the change in the energy that we predict by doing all the quantum mechanics is precise. We know exactly what energy corresponds to a molecule slowing down its rotation. And we can use this. So that's a lot of nice theory, but here's how we actually do this in practice. So if you're a molecule out there in space, so if you look here in the upper left, you're rotating really fast, you're hot, you have tons of energy, and you don't like that. You want to slow down to a slower state like this. You want to go from the fast rotation to a slow rotation. The only way to do that is give off that energy. And you're going to give off that energy in terms of a packet of light, photon of light, that here I'm labeling this symbol V transition. And you're going to do this, you're going to lose that energy, you're going to give off this photon of light. And if you happen to have your telescope pointed at this patch of gas, here's a nice giant radio telescope, we'll receive that light. And what we might get is something that looks like this. Here on the x-axis is the frequency. It's also approximate. It's also related to the wavelength of the light. And on the y-axis here, you get how much light. And you notice most of it is just kind of a scatter, right? There's not much trend here until you get to one particular frequency, which is this one right here. And that's the same frequency that the molecule emitted its light from going the fast to slow state. So we only see a lot of emission, we only see a lot of photons at that particular transition. So if you have enough molecules all slowing down their rotation at the same time, all emitting precisely at the same frequency, what that will show up in your observed astronomical spectrum is something like this. You'll get a ton of light at a very, very narrow range. And then outside of that, you'll just get noise, nothing else. the key here is then if you have some idea of, based on quantum mechanics or based on laboratory work that folks do, if you have a list of these frequencies and which molecules they correspond to, you can then go ahead and ask them, okay, I saw this peak here. What molecule does this have to be? And by comparing these spectra that we see to all of the reference data from the laboratory work, for the theoretical work, we can uniquely identify which molecule it was that was undergoing this fast to slow rotation. So if we put all of this together, it lets us identify what molecules are out there, what molecules actually cause this peak in light. So that's the nice story for how we actually do this. Just to show you some real data, that it often is quite complicated. Instead of having one peak, you might have hundreds, and they're all different molecules contributing. And it isn't just necessarily one peak per one molecule. One molecule can have many tens and tens of peaks. And so often the spectra you get look something like this. So this is the same picture. This is the same idea that we use. It's just a bit hard to, sometimes in very, very rich regions with lots of interesting chemistry, it's hard to pick out which one is uniquely different molecules. I think in this spectra still state of the art, I think there's about 50% that are still unidentified, the peaks here.
That gets me to another question, Dr. Law, if I may.
Yep.
When you were going this, I was kind of thinking, how we use spectrum to identify chemicals. We all have reference to stuff that we know about, spectrum of stuff that we see on Earth. You mentioned earlier that we've identified several molecules that do not exist on Earth or can't, probably because it's too energetic. So how do you figure out that you've discovered something new, or you just kind of either work backwards to say, this is something I don't know, and here's what the properties probably are? And the other thing, I guess the second question that's separate, I'll just throw it out there, is do you ever get issues with that? Like you're looking at a dust cloud, do you have to be real secure at the distance due to possibly like redshifting of some of these wavelengths? Because I could see how that would throw you off, especially at these low energies, and they're very packed right here. I mean, if you're off on your distance a little bit, I could see that being problematic. So
yes, those are two great questions, things that we do confront all the time. The first one is about the really exotic molecules that we don't see on Earth. The gold standard is when you can make it in the lab and you can compare. But when you can't, you can do a set of theoretical quantum calculations where they're not going to be always as good, but you can make predictions for generically any molecule that you're interested in. And it turns out the quality of the astronomical data is actually sufficiently good that we can kind of do what you suggested, where you can get an initial prediction for some new molecule and then actually use the data itself to improve your model, which is cool that we can actually do that. You're using the real data to actually improve your model, which is, I think, a fascinating thing.
Oh, so they'll see it, make a prediction, and then go try to find the molecule.
Yes. Yeah, that's what people do. There's sort of two people. There's like a group of observational people and there's a group of theory people, and they talk to each other and they're like, you should go look for this molecule. Or the observers say, hey, I have a peak here. What molecule is this? And there's this like constant feedback going on. Exactly.
Okay. Awesome.
And your second question, the redshift itself is not so important because a lot of these regions are very close. They're within our galaxy. They're actually very near in our galaxy. So it's not like cosmological redshift that we have to worry about. It's more important to know what the gas is doing, because this makes it seem like all of those clouds are just one unified coherent mass, all moving together. But sometimes there's like 3 or 4 subclouds all moving together. Sometimes they're hitting each other. Sometimes they're moving in different directions. And having a precise knowledge of that, being able to disentangle what all the clouds are doing, is important, because you could have the same molecule just sort of, overlapping each other, and you could be tricked. You could think it's a new molecule, but it's the same molecule just in 2 different clouds at 2 different distances. So absolutely, you have to pin down your physical structure before you start any of this. Yeah, no, wonderful questions. Yes, that actually touches on a lot of problems that we have to handle. Great, okay. So now that I showed you some real data, and we can now move on to what do we actually learn from this? This is great to know there's molecules out there, great to see spectra at tons of peaks. But what have we actually been able to take away from understanding the universe from a sort of molecular perspective? And I'll just first go back to this gallery, which is definitely not exhaustive. There's hundreds of other things you could do with molecules in astronomy. But I just want to talk based on time about one, which is the near and dear to my heart. That is these planet-forming disks. I'm most interested in how we can use these techniques to understand where our own solar system came from and how life ended up originating here and perhaps elsewhere in the universe. So I'm going to focus on this environment here for the rest of the talk and tell you a little bit about what we've been able to use molecules to understand about how we form planets. So as a quick rundown, the sequence of forming a planet originates in a so-called protoplanetary disk that is a natural consequence of the star and planet formation cycles that is shown here. What you end up having is that giant molecular cloud, which all the chemistry that we were talking about earlier on, that's why they have the name molecular now, but hopefully you can, when people talk about molecular clouds, you can know why. That is because you have all that great dense gas forming molecules. That's the first phase. You end up having the cloud collapse due to its gravity, forming a protostar, and around that protostar, you end up with a flattened rotational disk. Just because of the physics involved, because you need to conserve angular momentum, you need to be able to funnel material onto your young star, the disk ends up actually spreading out. And you end up something that looks like this, and we call them protoplanetary disks because they're the last stage before you actually form a solar system. So we had something that very much looked like this in our solar nebula. And it's the fact that you have all the material in this really thin disk that really facilitates planet swarming because material can start running into each other. And if material runs into each other, it can grow into bigger and bigger bodies. Yeah, and then the next stage. And once this is gone, this lasts about a few million years at most, this disk phase, and then eventually all that gas and dust is either incorporated into planets, incorporated into the central star, or just blown away out into interstellar space. And then you just end up with something like our solar system is now. But if we zoom in a little bit, I can just show you a quick view of what the structure of one of these disks look like. All of the planets we expect to be forming in the very middle region. That's where the densities are highest. That's where material is just hitting each other, forming the planets. We've been able to sort of map out this structure in detail. We can tell you where we expect the most gas to be, where the dust is, depending on its different sizes. The large dust ends up falling into the middle region and seeding planet formation. And so there's a whole industry of folks that study these disks, myself included, in detail. But the main parts here are that really you just have a central star, you have a planet forming zone in the middle, and that central star is growing at all times. So two things are happening. Your central star is growing and your planets are growing, and they're almost competing with each other during the first few million years. And eventually the material is going to be gone. It's going to either go into the star, it's going to go into the planets. And this is a very quick, in an astronomical sense, quick phase. But the thing that is most interesting to me is that this is the last stage before you make a planet, which means if you can understand the composition of these disks, so what they're made out of, that means you can understand something about the composition of the planet that will form and the atmosphere that will be associated with that planet. All of that is going to depend on the type of chemistry, the type of gas that you have in that disk. So here's just a beautiful artistic rendition of a young forming planet in one of these disks. And you can see it's absolutely bathed in dust and in gas. You can see here, if you zoom in, you actually see a smaller, tiny disk with moons forming around a giant planet. The idea here is that if we look at the molecules in these disks, they can tell us something about how planets should form and even how our own solar system forms. And so that is the game that I play. That's where my focus is. Mostly, I use this telescope here, which is called ALMA. It's the Atacama Large Millimeter Array. It's a giant array of 66 antennas in northern Chile. One of the more expensive, most expensive ground-based projects. But the key here is that it's incredibly sensitive because you have so many dishes, and it's incredibly high resolution. This telescope has a resolution 5 times that of Hubble, because you can just take your antenna, you can put them nearly 10 miles apart, and then you get a telescope that is around 10 miles in size. and they can actually be moved around on little carts. You can actually change the whole configuration. So you don't just get one telescope, it's a dynamic telescope that changes all the time. And here's just a quick view of a few of the antennas, the central core. But you can really take them and separate them up to a maximum distance of 10 miles. So you get a really fantastic view of what's going on in these otherwise really tiny disks where planets are forming. But the main focus here actually is not on necessarily the fine spatial resolution we get, it's on the sensitivity. We have 66 antennas, which means even in that thin little disk, we're able to detect the gas, we're able to detect molecules. And I think we're not able to detect those huge molecules out there in interstellar space, but we're able to detect around 30 plus now. And what we've been able to see is that we find things with nitrogen, we find things with carbon, with oxygen, with sulfur. Many of them for the first time discovered using the ALMA telescope. And I think that this is a growing literature, very active field right now, people studying these protoplanetary disks. I touch on two quick advancements that we've made, two discoveries over the last 10 years that really have excited me. And the first one is the detection of complex cyanides in these disks, and complex in quotations here, complex for us astrochemists. These are molecules with a few up to 6 atoms. What we see here is in this gallery here is an actual image of these disks. The blue here corresponds to the light that we got from that molecule. We detect the hydrogen cyanide, the HCN molecule, as well as the HC3N and the C3HCN, which is called methyl cyanide. But the whole point is that these are largish molecules with a cyanide group, the CN attached to them. And sort of at the same time, these discoveries were being made with ALMA, with our telescopes, other folks were showing that one of the very first steps to making biologically relevant molecules, so sugars, amino acids, nucleobases, can actually start with cyanides. So the fact that we're able to now detect many different cyanide molecules in these other solar systems that are going to go on to form other planets in the future, they match very well with this prediction that they have the chemical ingredients necessary to go on and make more complex and potentially life-sustaining, life-supporting, larger complex molecules. So that was very exciting because for the first time, we can actually start to address this origins question in detail. We can say, okay, is the chemical ingredients for life, is it there or is it not? And at least in these systems, it appears that it is there. So this was a study from 2015. It was the first detection of these complex cyanides. And a follow-on study, what we're able to do is confirm and expand these detections. We found them in more of these other disks that are out there. You can see the 3-color image here at the bottom is 3 different complex molecules. The top row here is the dust. So what you can think about that is where the planets are actually forming. And each one of those gaps you actually see in the dust could be a protoplanet that has formed and carved out that gap. If you draw on this, where we'd expect the comets to be, if these looked like our own solar system, you can see that in the middle row here with the dashed line. So if you put this all together, what that means, we're detecting complex molecules throughout a disk where planet formation looks like it's happening throughout the entire comet reservoir. And if you remember, one of the very first images I showed you was this, where the scenario of life that perhaps started here on Earth was via this delivery of prebiotic molecules from comets that came in close, got heated, and then deposited those prebiotic molecules onto Earth. We might be seeing an analog to that here, where all of these other disks that are going to go on to form other solar systems that might look like our own solar system seem to have the very same chemical ingredients that would be needed to seed life, very much like it did on our own solar system. And so I think this is an incredibly exciting time because we're able to actually start quantifying and testing some of these predictions. Okay, so with that, I will just wrap up with my very last slide, which is to just touch on what I think the future holds. And to call back to that plot where I was showing you the cumulative number of detected molecules. And what I suspect is that this line is not going to flatten at any point soon. And in fact, I think in the near future, this will only continue to increase. That is, we'll be able to detect more new molecules at an ever increasing pace. So I looked this was actually maybe a month ago already. There was 3 molecules that are already been detected this year. I suspect I'm a little behind on the literature. My guess is it's probably 5 or 6 already this year. And we are poised to have many major upgrades, both to ALMA and to other telescopes that will add a similar bump in the detection statistics here. So all this to say, I think there's a pretty bright future ahead for understanding molecules in space and for using those to learn about fundamental questions such as our own origins. So with that, I'll just say thank you very much for your attention. And if you're interested in astrochemistry, I think that there's quite a bright future for all of us.
Thank you so much, Dr. Law. You have time to entertain questions from the group, other than Rich?
A quick question about benzene ring, organic chemistry. Is there any kind of molecule like that found so far?
Yes, a great question. There has been, yes. So there's been a benzene ring detected in a molecular cloud. There's actually been a few rings, 2 or 3 aromatic ring structures detected, and all of this within the last few years. And that was sort of what I was alluding to one of the previous questions, where people thought that you wouldn't see these huge molecules, benzene rings, out there in these cold quiescent clouds, but you do. And so it seems like it's really just a telescope question. If we look longer, we find more and more complex things, and we're not sure where that ends, right? We might end up finding 5, 6, 7 aromatic rings. So yes, we definitely see these benzene rings. Technically, it's not benzene, it's benzodiazide. We need to substitute one of the groups so it actually has a rotational signature. But yes, we definitely know that it's there.
Dr. Law, 3 questions real quick. I saw in your one display chart, you showed that your radio telescope dish, but you said the light emission or the light signal is the full spectrum, I guess what used to be called the radio frequency spectrum, and part of its visible considered light in terms of nomenclature?
Yes, I would say that any photon is light, and you could have radio light or optical light or UV light or X-ray light. I would call it all different types of light. Yeah.
How does the antennas that you use down in Chile compared to the ones, the very large array in New Mexico? Do you use that one as well? Or is that dying or?
Yeah, so it compares very well. They actually operate at slightly different frequencies, so they're complementary to each other. Right now, I'd say ALMA probably has a marginally better sensitivity, but both facilities are expected to be upgraded soon. ALMA is undergoing its upgrade now, and then the VLA, the Very Large Array, is poised to have a transformation into the next generation NG VLA in the next decade or so, which will make it even better than ALMA, essentially. It will be a telescope that will span pretty much the whole North American continent. So we're really excited to look for that upgrade. It's just a little bit off in the future.
And my last question was, obviously we have a boatload of water, mostly water. Has your research figured out why we have so much water, or is that prevalent everywhere? It just has to be in the right space, I guess the Goldilocks zone, or any thoughts about why we have so much water and why it's so necessary, I guess?
Oh, yeah, that's a good question. So we can detect water throughout a whole set of astrophysical objects. And in fact, very recently, we've actually been able to find water in these disks themselves through a variety of different techniques and instruments. So it does seem like water is actually ubiquitous across different systems. So we might not be wholly special in that regard, which is great for life. If you want life to exist elsewhere, it's nice that other systems have similarly abundant water. In terms of the water being in the right phase, you referred to the Goldilocks alone, that has to do more with you'd want your planet to actually have liquid water and not all be ice or not all be vapor and flying away. So that's the second question. You need the water, and then you need it in the right form on the right planet. So water alone won't mean life in these systems, but it will be nice. It's nice that we can detect water everywhere. So we maybe are not totally special in that regard.
So you're finding water everywhere. It's prevalent.
Yeah, it's fairly prevalent. Yes. So,
water everywhere. Now drop a drink. Yeah. Thank you. All right. Thank you, Dr.
What type of questions are you hoping to answer with all this new data?
oh, so that's yeah. I guess it depends on who you ask. that you can use molecules, these kind of spectra, to learn about a huge degree of things, right? So I talked about the planet formation and where we think life comes from, and that's something that sort of I'm most interested in, but there's a huge number of folks that don't care about that and use it to do something totally different. There are people that use it to map galaxy structure. There's people that use it to learn about how stars actually die, the supernova process. It really depends on what your aim is. And so one data set, depending on who you give it to, can learn a totally new thing. So I'm most interested in touching on those questions of origins and are the chemical ingredients for life there. But many other people want to use that to understand more about physics, per se.
If I may, you also mentioned the transition where you have A plus B equals AB star, and then it breaks down. It seems like that would probably give off a very different energetic signature. Is that useful, or is that just too noisy because there's no control over how that AB star breakdown takes place?
Yeah, that is a good point. It's not as coherent enough. I mean, we really need something that is really coherent and identifiable, because even in these really, like the spectra I showed, which had 700 lines, like that's even, all those are very coherent coming from different transitions, and we're already struggling. We don't know what 50% of that is. So we're going to have a hard time finding those signatures if we're already struggling with the ones that are very nice and predictable.
Dr. Law, one last question. We had a planetary scientist present to us, I guess, a few years back, and you know, the question of life came in, and he said, if I remember correctly, he said that, well, the more we know, the farther out we see, the more we realize how lonely we actually are, and there's really not much out there. Any thoughts on that from your research? And you know, it's been several years since I've heard him say that, but any truth to that? Where the more we realize how unique we are out there.
Oh, that's an interesting question. I mean, I guess in my personal opinion, and from what we've seen, is that it tends to suggest that maybe we're not that unique in terms of the type of planetary system we are, with potentially access to the same sort of chemical reservoirs. I think that we've found other systems, other young solar systems that could look similar to us. Now, in terms of making that next giant leap about, say, life elsewhere, then I maybe tend to agree. I think that getting any sort of direct answer to that is going to be very hard, because we're just so far away. And anything that we do is inherently an indirect sort of measurement. So that's why I talk about the chemistry that comes before life, because that's something maybe we can assess. I think, yeah, to a degree, distance is going to be our biggest problem, right? Even if we find some interesting signature somewhere, it's probably not going to be able to send a probe outside of our solar system to go see. So I think it's both. I think we don't have to be so pessimistic that we're just totally alone, because we're finding these nice hints that maybe we're not. But confirmation is going to be a whole nother ballgame.
Still swimming in the first couple of factors of the Drake equation. We have another question in the back of the room.
How is the time for these processes to take determined? I mean, is there like another study that determines things take millions of years?
Yes, I guess that sort of referring to the lifetime of the planets forming and the disks surviving. There's been a lot of work on that to actually figure out how long this process takes. One of them is actually, you can sort of count. You can go to different regions of different ages, and you can count how many disks are there. And then what you'll end up seeing is that once you hit a certain age, the number of disks just drops off. That by a certain age, that pretty much the typical young star doesn't have a disk anymore. And so people have done this on a statistical basis and can give you sort of the average age that you know a system will be before it forms all its planets. Now, pinning down that number in detail for an individual system is very difficult, because there's lots of variation. But at least in a statistical sense, we have a pretty good idea of how long these things take.
Any other questions?
Is artificial intelligence kicking in now? Still analyzing your spectrum, so you guys are like taking it to like the next level, putting it on the turbocharge now?
Yes, I think that is just sort of starting, where the community is sort of ingesting these new techniques and now trying to apply them to these spectra, because we definitely need help. It's quite complex, and AI can help us a lot. And I should say that the upgrades that we're expecting as a field is actually going to make this problem a lot worse. We're going to get a ton more data. So I think it's a perfect time for AI to be where it is. We'll make use of it.
Well, I'd like to ask for another round of applause. Thank you very much, Dr. Long.
Well, thank you all so much for your attention and for spending the evening together. Hopefully this was informative. Yeah, happy to be here, and thank you again for having me.
We were thrilled to have you. Thank you so very much.
Okay, well, hope all of you have a great rest of your night and evening.
Thank you very much. You're welcome to join us for the rest, but the rest of it's going to be a little bit more boring. So thank you very much.
Okay, I might head off then. So thank you.
Totally understand. Thank you. All right. That is
Real cool. Good job.
Pretty big.
yeah.
Thanks for putting that together.
Oh, no, it's actually courtesy of our friends at NASA. It's one of the benefits that we get for being a active club in the Astronomical League. Sorry, in the Night Sky Network, doing all the outreach events that we do gets us some perks. We get occasional handouts, we get occasional giveaways, and we occasionally get a reach out from the folks at NASA to see if we want a speaker.
So they reached out to us.
Yes, we got offered the spot to have a guest speaker, and we seized on that to get Dr. Lodge's. So let's by all means the work that our great club vice president and the outreach crew do to help the local area also helps us get more opportunities. Yeah. So I'm going to defer observing reports tonight, but I do want to give an opportunity just for a couple quick items of new business before draw door prizes and adjourn. As far as I know, we don't have any old business that hasn't been covered other than Ben's award. Bruce has left us, but one of the great things that he does for the East Coast Star Party is get us a lot of great door prizes. In order to do that, he needs money. And in order to give him a large amount of money to buy said door prizes for the East Coast Star Party, or to authorize that, to allow us to go that keep us about breaking even, we need to authorize that money. Traditionally, we had last time we gave him about Bruce a little over $700 to buy various prizes over the course of the year. If we wait until the last minute, he buys things from High Point Scientific or other places. If he gets them a little earlier, he can sometimes snap up deals in the meantime. I would like to introduce the idea, if the membership is interested and willing, to go ahead and authorize a budget for the next East Coast Star Party. With the comment that I don't think I can propose the motion, but we've previously given $750. If anyone has any thoughts, blatantly shaping. Gabe.
Well, last time we were here, we were left. I think so. Like I think 600-700 is a fair value because that means that because like last time we were there, like there were items left over that were saved for later, and it's better. And like it's like even if we don't sell all the items that are purchased, we can always just put them into the door prize pile for next time.
Excellent point. And also, if there's an interest, I've used various options on how to get door prizes for our club meetings. Sometimes they're really cool. Sometimes I get donations. Other times it's a little bit more scraping the bottom of the barrel. So we could also share those between those. Yeah.
I move we authorize $700 for this purpose.
Okay. There's some discussion.
I move we double the 700 to 1,400.
My
Money. We can break even. What's the problem?
My question was, inflation wise, back to Rich in terms of what money's available, if we count discretionary that aspect, and then is there a sweet spot in terms of inflation, whatever was auctioned off or given away as door prizes last time, now it's not 5-10% more expensive. And we've lost Orion. What was the Orion telescope?
Orion and me.
Yeah. So there's more expensive stuff left.
I look at it this way, and that may be a problem, but we do have quite a bit left over. So if we authorize a budget for Bruce, he can manage it. Like, and the reason we're doing it early is so if there's like a sale, he could maybe get some stuff. And if he needs more, he can always come back and request more. That has happened in the past. But by this, we're just giving him the authority to go ahead and buy stuff he sees fit. He doesn't have to use it all. Or he may say, I don't think I have enough. Maybe I need to be more. He can come back and ask for more.
So do we split the difference?
So we've had a motion for 700, a thought to double it to 1,400, a compromised offer of 1,000.
There's a lot of news lately that astronomical manufacturers have increased their prices a lot.
That's true.
So just be aware that money is not going to go as far as it.
When I came to the dark side, my C Star cost me 550 instead of the 500 people been buying them at. So that's a fair point.
Inventories are kind of weird right now.
That's a fair point as well.
But their prices have gone up.
Put a round number, $1,500 out there, is it too much?
Gone even further up.
Oh, yeah.
Well,
so-
the other thing you have to consider if we start taking the door prize money up is, we do have obviously a fair amount in the treasury, but the whole point when we took on East Coast Star Parties, we wanted it to be revenue neutral and not be a liability to the club. And based on the, we did some testing. I built some, we've kind of figured out what we can spend and be right at that point. So if we start jacking up the amount that we're looking for door prizes, one of two things happens: either the club's subsidizing, or we have to increase registration prices.
It sounds like Rich is suggesting that if we stick at 700 for now, and if Bruce needs more money, he asks for it.
Disagree.
Okay.
Yeah, we've never had this much money ever since I've been here, and probably ever in the history of the club.
So due to the late hour, I'm not going to go into too many details, but there are a lot of other things that as a 501c3 nonprofit club that we can do with some of that treasury. That's true. And that's why we can refund some of that into the community with funding our own library telescope programs and the like.
Great.
Because you have money, but because you have money as a 501c3 does not mean you have profit.
True.
It's two different things. Just because you can have a $1 million budget, it's not profit. We're not.
But our balance
profitable.
is increasing. It's increasing.
The balance is increasing.
Yeah. So I definitely don't think we should raise
Inflation.
the dues anymore.
No, but
That's the last East Coast Star Party that I was at. Every single person got a door prize. So it's a little bit paradoxical to have a door prize when everyone gets one. As it turned out, the highest prize was never even given because everybody else had gotten.
we did have a lot of people depart prior to. Yeah, that's a
So
fair
it's
point.
a little hard to have a door prize when everybody gets it.
Okay, so how many door prizes were left over? You know?
2 large door prizes and a smattering of small.
Why were they left over?
Because we had
We didn't have enough people for them all.
a lot of folks left early because it was cloudy.
So do we need to have any door prizes then?
Well-
To use what we had last time?
We have we're going to modify the plan to give the door prize tickets out at the drawing rather than having
Okay,
Yeah.
earlier on, gotcha.
Tickets were given out Friday, Saturday,
too early.
drawing, Thursday, Friday, the drawing was on Saturday.
Lessons
So
learned.
some of those people had already departed.
Yeah, because the weather and so people left. But see, that's another thing is like, do we need more budget? Because he's probably going to buy less stuff.
Fair.
We have leftover things that we're just going into the booty for next time.
I would rather have 1 or 2 or 3 large prizes
Me too.
rather than a whole bunch of little ones that don't mean as much.
That's perfectly valid. So that's something we'll bring to the committee.
Yeah, that's something else we've kind of debated about. Is like, do you have like 1 or 2 really good prizes? It's hard to buy, that to know specifically what someone want, but it's also hard to find something that like has universal, it's kind of universal. Anyone could, but then it's like, I already have it, or something like that. Or
That's my piece, come on now.
I'm like, you got eyepieces. Yeah, none of them are as good as my eyepieces, but I can also give them to somebody else.
There has been a second for the motion on $700, even though I know Jeff is going to be
Like to
upset.
amend the motion to 1,500.
There's been a motion to amend the motion, which I think, I don't have a copy of Robert's rules on me, but I think that's in order.
Well, he has to get a second on the amendment.
That's true. Thank you, parliamentarian Rich. And I think that the amending motion dies for want of a second. And due to the,
second to first one?
yes, the first
I did,
700.
I did too.
You
Is
put it
there-
on the table, I second it.
Further discussion? In that case, all in favor of the $700 budget, which can be amended? All opposed? I was expecting a nay. Ayes have it. Motion carries. Bruce has a budget. I'll tell him about it in the morning. All right. Out of respect for everybody else, I got 2 more items. Discussion of boardwalk astronomy T-shirts. Do we want to discuss that this evening, or do we want to table it to another night? I'm looking at Sean because he's the one who's responsible for action on it, and also the stuff.
We're not going to have it on boardwalk.
Check.
So we're going to let you.
Okay. All right. And there was a recommendation made about, since Jeff does such a great job of making our club passes. A great suggestion from Sergio was to also make some lanyards for the club. Poking around, we found that we can, for about $400, we can get about 350 lanyards. That would be whatever color. I suggested blue with white lettering, say Back Bay Amateur Astronomers. We can give them out to club members, sell extras, etc., so that we have something that's easily identifiable.
Glow in the dark?
What's that? We could potentially make them glow in the dark. That's definitely an option. I don't know if there's any interest. We can also table it for another time. Sorry?
That sounds like a good idea.
Okay. Any thoughts, discussion?
Move to get lanyards.
Move to get lanyards.
Second.
With a budget of not to exceed,
With a budget
or just
not to
whatever amount I feel like.
With a budget not to exceed $400.
Okay.
We give them away as
I-
our prizes.
Too soon.
All
right.
This many club members.
That's fair.
We have
You
188.
want to say as many as somewhere over in the 300 to 500 range for not to exceed $500? Give us a little discretion. Is that acceptable?
Yeah, 3 to 5.
Right, get more. Can
3 to 500, with the intent of buying, at least enough for our current roster.
all right. Do I need to repeat that? All right, so moved and seconded, $300 to $500 with enough to roster. Any discussion? All in favor? Any opposed? Motion passes. We'll get some lanyards. All right. That is all I have prepared for new business. Is there anything else? We're 5 minutes over. All right. On the door prize. All right. So tonight's unfortunately one of the less exciting ones. I tried to make these thematic. I couldn't come up with anything that's appropriate for stellar chemistry, but everyone always needs a red flashlight. I don't know how many times I've left home to go observing and haven't had one. I hope someone will, as a result of tonight, not find themselves in need of that. This one actually, I think, has some multiple settings. So, the winner of the Astronomical League Award recipient will be our drawer, yes, that's a word. Number is 089.
Missed it.
089, all right. All right. Okay, well, with that said, that's all I have prepared. With that said, I would like to entertain a move to adjourn. All in favor? We are adjourned. Thank you all for coming out tonight. I hope you enjoyed.